Hey, good morning. Welcome back to science class. Today we're going to discuss the difference between molality and molarity. Yes, molarity, the way we measure the concentrations using the equation moles over solute, right? That's what we use a lot in class. We used it all last week to mix up those solutions. Molarity, the big capital M. We see it everywhere, right? And today we're going to talk about molarity's little brother, or molarity's little brother, molality, and molality with the little m, and molarity with the capital M. That's the way we tell them apart when they're written on the paper. So let's look at the equations and let's compare it. Let's go to our one we're familiar with first, molarity. Molarity, capital M, is moles of solute. That's the amount that's dissolved in it. Moles of solute in liters of solution. This is where we need to have the volumetric flask to make these solutions. That's why we need that. We need to know how much solution is totally made at the end. And the reason we need that is because it is something we like to use for factor label. Factor label. Right? If we're working with equations, if we're working with stoichiometry or factor label, we need to use molarity. That's what it's designed for. So we can know how much material we're using in the reaction. Opposed to that is molality. And molality is going to be moles of solute over kilograms of water. So it makes it a little bit easier to measure some out. If you can measure out a kilogram of water and put some stuff in it, right? And you know the volume's going to change with that because the water's going to shrink, or we're adding material in there, so the volume's going to change, but that doesn't matter anymore. We're worried about the mass of the solvent. It doesn't have to be water. In our case, we're going to use water every time. And its label again is little m. It works great for certain things, but it's not the factor label. It's not usually for factor label and balancing equations and that kind of thing. It's not going to be for that kind of chemistry. It's for a little bit different kind of chemistry, and we'll talk about that in a second. So we're going to come back to molality. There's the difference at kilograms of water instead of liters of solute. It's backwards on my screen. Kilograms of water versus the liters of solution. All right, let's look at what this molality is used for. What we call the colligative properties. The colligative properties are how a solution's properties change as it becomes more concentrated. Let me say it another way. As you have a pure solvent, so you have water, it freezes at 32 degrees Fahrenheit. If we add salt to that water, the temperature which it freezes will drop. This is why we add salt to the roads in the wintertime, to melt the ice. Well, what we're really doing when we're making a salt water solution or a ice salt solution, and the temperature which it freezes will be lower. The more salt added, the lower the temperature goes. Now, there's a limit because only so much salt can dissolve in water. If the temperature outside gets so cold, I can't remember what it is off the top of my head, then it's too cold that even the salt water freezes, and they know that's when school's canceled for sure. Right, it happens a few times. So freezing point depression is when the solution freezes at a lower temperature than the pure solvent. And our example, again, was salt water on the roads. Now, also when you used to make ice cream, if anybody has the old hand churner ice cream, right? Same thing. The salt in the ice makes the temperature much lower, the temperature it's freezing at, so the temperature drops well below the freezing point of what the ice cream mix would be, and it would freeze solid. So if you haven't made ice cream at home, we're going to do it in class, so if we ever get back to school, we'll do that at some point. Let's look at this equation really quick. Delta T, change in temperature. That little F down there, that means freezing, right? So the temperature of the freezing point, delta means change. The change in the temperature of the freezing point is equal to, Mr. Arnold, you're in the way again, is equal to the molality. There's that concentration, that molality. That's what we're going to learn today. Times Kf, which is a constant depending on the solvent we're using. In our case, we're going to use water. And then times I. I is the ions, because remember, ionic compounds dissociate. And so if it's a compound that has more than one ion, well, if it's a compound that has 2 or 3 or 4 ions, the effect of those particles in the water are going to change that temperature. Okay, now a lot of people ask me, they say, oh, Mr. Arnold, why does it do this? Remember, this is my water, right? These are water molecules. The O, and these are my hydrogens. It's polar. And it's lopsided like that. It looks like little Mickey Mouse ears, right? Actually, this really looks like rock and roll to me, right? Yeah. So we have the water molecule like this. When water molecules start to freeze, remember they have to line up positive to negative. Well, if you have, I'm going to use my snowball here as a solid particle. There it is, my little microphone. Now, if, say that this particle is dissolved in the water, right? It's in the way, right? The particles can't freeze because they have other little particles that are in their way. And since those particles are in the way, the temperature, which is the speed of the particles, the temperature has to drop lower and lower and lower until it can form that crystal structure that it wants to form. So it's interference. It's just interfering. The more particles in the way, the lower the temperature has to be. Another property would be the boiling point elevation. So boiling point goes up as the amount of solid gets in the way. And think of it as the same thing. Those particles are trying to boil. They're trying to escape. If there's other large particles in there that are in the way, again, blocking their path out of that liquid, it's their path into the sky, their evaporation, their boiling, it's going to slow them down. So the temperature overall is going to have to be higher before it will boil. So again, interference. If you just think of it as the particles of the solute are interfering with the solvent's normal abilities, you should be good to go. All right, the equation for this looks just the same, except it has a little b there for boiling. So the change in the boiling point is equal to the molality, that's the important part, times a constant, because every solvent's a little different, and then times I, because those number of ions in the way interfering with the normal boiling point is what changes that temperature. So, first, we have to look at molality. And so today's, hey, we're now in Schoology. So we're going to go into Schoology, into the remote file, the remote learning file. And we're going to go down to today's assignment, which is 1:13:22, molality versus molarity. Same thing we just talked about. We're going to open that up. Now, I've already opened it up to save us some time. And there's my problems right there. I notice I have my calculator ready to go because I'm going to need my calculator today. And so this is going to use molality, which is the molality equation. So if you want to copy, which is Control-C, copy that equation, and we'll paste it in right here. Oops, there we go. Make sure you're in text box there, and paste it in there. We'll be ready to roll. To save yourself some time, I would just go ahead and paste it all the way down. You know, you need it every equation, and that will save us some time, and it will also get you set up for the problems. All right, there's only 5 problems in this section. And our main rule, our main thing we're trying to do is match the labels up with, I don't know why this is showing up, there we go. Match the labels up with the equation. They have to match. Okay, number 1, what is the molality? That's that little m of a solution that contains 1.5 moles. There's our moles. So put the 1.5 with the moles. And I just copied it and pasted it, right? And then it says kilograms, 0.5 kilograms. So I'm going to copy that, and put that with kilograms. And that's the kilograms of water. So that's pretty easy to do. You just have to match it up. Now this first one's set up real nice because it's just normal. The m's by itself already. So all we have to do is take 1.5 and divide that by 0.5. And I got 3 as an answer. So the label's just 3m, 3 little m. It's a little m. Make sure you use the little one, not the big one. Big one's molarity, this is molality. Okay, real simple. The next problem you do will be just like that, set up the same exact way. All right, no problem with that. That's what I'm leaving for you. All right, the next problem here, number 3. I'm to 3. And the reason I'm going to number 3 is because they want me to solve for the mass of the water. That's the kilograms. And they give me the other information. So what I'm going to do is make sure everything fits where it goes. Dissolve 3 moles. 3 goes with moles, right? And 1.5 kilograms. Oh, I'm sorry, 1.5 little m. I almost messed up there. 1.5 little m. Put that where it goes. And now we're going to solve for kilograms. Problem. Kilograms is on the bottom of that fraction. We always need to have it on the top. Okay? When you're on the bottom of the fraction, I'm going to draw the picture. All right? I'm going to draw this out. You don't have to draw this out. I'm going to draw it out just to make it work. So there's one line. That's going to be my fraction in a second. And I'm going to put an equal sign with that. Now, I'm going to change colors because this thing gets weird when I use the same color. It keeps trying to copy everything. So I'm going to make this so it works out nice. So I'm going to put my 1.5 right there. I'm going to put my kg here on the bottom. Ooh, I'm going to change colors again. I take that back because if I don't, when I try to copy it, it's going to be goofy on me. Again, if you know what you're doing, you can skip this part. You don't have to listen to me jibber jabber about this stuff if you know what you're doing. So kilograms go on the bottom. And then again, I'm going to change it up again because I know how this thing is. And I'm going to put 3 moles on top. So I'm just going to put a 3 up there. Okay, now if I want to solve for that kg, if I want to get down there and do it right, remember what I have to do. I have to take it if it's on the bottom of the equal sign and move, oops, the screen's backwards, and move it to the top. If I have it on the top of it equals and I want to get it to the other side, I move it to the bottom. So what I'm going to do is I'm going to swap these 2 out. I'm going to take, I think he'll let me use I'll use this one. I'm going to take this, kilograms, and move it up here. I'm going to take this 1.5 and move it down here. And lo and behold, I have kilograms on one side by itself. And that's what I'm trying to get. So calculator-wise, hey, 3's already in there. 3 divided by 1, oops, never mind. 3 divided by 1.5 equals 2. And so you end up with 2 kilograms. Okay. Now, do you have to write it out like that? No. If you know how to do it with the equation, you can just look at the equation. If it lets me get to the equation, there we go. You can just go to the equation and say, okay, kg's on the bottom. I'm going to copy it and put it on the top. This little m's on the top. I'm going to copy and delete it there. And I'm going to move it to the bottom of the other side. So you can do it with the type. I just thought it'd be easier to see if I had it written out the first time. All right? And we already figured that answer out, didn't we? Yes, it was 2. So the answer was 2 kilograms. So next time that happens, and I'll tell you which one it is here in a second. Okay, we know what to do. What is the mass of the water? Okay. Oopsie, I got something I have to change. This one slipped past me. What is the mass of the water? So we're going to do the same thing we just did. Here's our problem here, all right? It says 0.500 kilograms. We need that in wait a minute. That shouldn't be a kilogram there. That should be a mole. So change this, change this to moles. Right, that goes with moles. So next time you do that, then solve for kilograms, and that was the mole number there. And you're going to solve for kg just like I did in the problem above. You know what? The labels are in the right spots up here. Now the kg's there. Moles on top. Little m's on bottom. It's set up for you if you're not sure how to move them. Okay? All right. So number 4, I had a little mistake there. We got that fixed. All right. Number 5. How many moles? This time we're solving for moles. All right. So how do you solve for moles? It should be set up pretty nice. Moles are on top. We want to get that kg away, remember? So let's put everything in the right spot and see if you can do it. So we have 2.4 kilograms of water. Copy, paste, and 1.2 little m, paste, right? What do? We're solving for moles, so we're going to take this on the bottom and bring it up top, so 2.4 times 1.2. 2.4 times 1.2. Remember on the bottom we move it to the top and I got 2.88. And that is M. Oops, that is MOL. Moles. Right, that's it. That's the problems. Do the 2 I didn't do, and submit. Thank you.